Hey guys, in this video we're going to look at solving ODEs with MATLAB. So let's go ahead and jump right in. So before we hop into MATLAB, let's talk a little bit about how numerical integration works. The only disclaimer I would give is that this algorithm I'm going to use is going to be much simpler than the one that MATLAB would use under the hood, but the general idea should be the same. So we define a differential equation x prime of t equal to 2t with an initial condition of x of 0 is equal to 0. Then by integration, we can come up with an analytic solution that is x of t equals t squared. And then we can just directly analyze that, but to take a numerical integration approach, we can start at t equals 0, which is x equals 0, and then we can take a step over, some delta t. Let's say that's equal to 1 for this case. So now we're going to be evaluating x of t at, or x at 1. So x of 1. And we're going to do x at the prior point, which in this case is x of 0, plus the length of the step times the differential. And where we evaluate the differential is a choice that you make in your algorithm. In this case, we're just going to evaluate at our new point, which is x prime of 1. This is one of those places where MATLAB could be a lot more accurate. This is equal to 0 plus 2, which is equal to 2. Now we can compare that over here to the analytical solution, which is that at x of 1, we should have 1. So you can see we've already had some drift. But let's keep going. So we'll plot that out right here. So we look at x of 2. So this is taking another step over of value 1. That's going to be equal to x of 1 plus our delta t, which is again 1, times x prime at 2. So now it's going to be 2 plus 4, which is equal to 6. And analytically, we can look at x of 2, which is going to be 4. And we'll do one more. So that's somewhere up here, right? So x of 3 is equal to x of 2 plus delta t, x prime, and we're doing it at 3. And so now we've got 6 plus 6 is equal to 12. And similarly, analytically, we can do x of 3, so that's going to be equal to 9. And there's been quite a bit of drift here. So how could we make this more accurate? Well, the first and simplest thing is to take delta t and make it much smaller. So if delta t were to be equal to 0.1 instead, so if we looked at x at 0.1, and that would be 0 plus that's supposed to be a multiplication there. And so 0.1 times 0.2 is 0.02. If we compare that analytically, you can see that our we're still pretty off, unless I did some math wrong there. But you could get a lot closer. Now another reason why this is so far off is because we're evaluating the differential at our current point. So when we were at x equals 1, we were evaluating the slope here. But really, that's looking at that. But there was this entire region that we know had various other slopes. And because we're only looking at one point, we're going to get some inaccuracies. It would be better to look at it probably somewhere in between our step size. So if we were to take another look at that, then we could say, let's do x of 1 again. And let's say we look at in the middle of our step. So we look at x at 0.5. And that's equal to 0 plus, now if we go back up, it was 2t. That's equal to 1, which actually in this case happens to be the right answer. So let's see if we carry that forward, if we can continue to get some better answers. Or delta t, we're just still keeping it at a solid 1. So now that'll be at 1.5. And you can see we're actually hitting the mark now, which is not necessarily going to always happen. It just happens to be happening for this function right now, which is super convenient. So this is one of the things that MATLAB will do. It's intelligent as to where it takes the differential. The other thing that MATLAB will do that's different is that if you were to plot out the actual function, the final result, and let's say it looks something like that, and then it's got like this really jarring change and it's kind of flat. So all through this lower region down here, MATLAB can take relatively large step sizes and still stay accurate in the way that we were. And so it'll keep doing that, and it'll get to this point right here, and it'll take a step there. And it'll notice that there was a large discontinuity. It was not very smooth in that region. So then what it'll do is it'll take its step size down. So maybe it'll try next right there. Still too much change, so it goes there. And so it'll take these small steps over the region, allowing it to be accurate. And then once it gets back to a flat region, it'll notice that values aren't changing very much, and it'll start to increase its step size back out. And that's how it's able to efficiently handle things. Now it's important to note that if you were to have something that was a bouncing ball, so let's say that we've got y over here and t over here. And so our bouncing ball looks something like this, right? Then there are these little discontinuities down here. In theory, MATLAB can probably get over them, but it's going to be very slow to do so. So you're going to have to think about that when you're designing your problems and putting them into MATLAB as to how you're going to handle these sorts of events. Okay, so now let's try to take the same function we were just working with and put it into MATLAB. To do that, we're going to use the ODE45 function. We're going to use ODE45 as our starting place for almost any ODE problem. It just kind of handles most things. Sometimes it won't work. The first thing to do is going to be to define a function that describes our dynamics. Now remember, our differential equation is simply x prime of t equals 2t. So we'll define function dy dt equals, we'll just call it dynamics of, and then the inputs to this function are going to be t and y, like that. And essentially what this is going to do is ODE45 is going to take this function, it's going to repeatedly evaluate it in the same way that we were evaluating things by hand, and look for the output. So dy dt is just going to be a single element long, right, because we only have a single function, and that's going to be 2 times t. And that's it. That describes the dynamics of our system. So then we're going to go ahead and run ODE45, which gives you out a time and a value vector. And that's going to be ODE45. And to do that, we're going to hand it in the dynamics equation. Now notice I used this @ symbol. That @ symbol allows MATLAB to store a reference to the function instead of calling it right away. And then the ODE45 functionality can keep calling that function over and over again. We then need to run over some sort of time span. Let's just do 0 to 5. And we need to give our initial conditions. Remember we said that x of 0 equals 0, so we will do that. And that should be it. So let's go ahead and try to run our function. I need to save it. I should have suppressed my output. Great. So we've got some values t and y, and we can go ahead and plot t and y. And we can see this is what our result is. Now it might be interesting also to compare that to the analytical solution we found earlier. So we'll plot the same t's, and then we'll just plot the analytical solution was t squared. And so now we can compare our two windows and see that they are in fact the same. Okay, so that was all nice and easy for a first order differential equation, but the way MATLAB works, you can't give it second order or even higher order differential equations. You have to give it first order differential equations. So what if we have a function y prime of t, y double prime of t, sorry, is equal to t with initial conditions y of 0 equals 2, y prime of 0 equals 5. Well, again, we can come with an analytical solution by integration. Okay. But to put it in MATLAB, like I said, you need to have it as a first order differential equation. So what we're going to do is we're going to define a state space of equations, y1 and y2. Eventually you'll think of these as being the y double prime, the y prime and the y of this general equation. Now to make that substitution, what we will do is we will define y1 prime equal to y2. Okay? And so now we can substitute, well, we can take the differential equation, or we can take the derivative of these two, sorry. So where we have y1 double prime is equal to y2 prime. And we can say that y1 prime is going to be our original equation, y double prime, right there. So that will be equal to t. So now we have our state space, which is y1, y2. And we can also define y1 prime and y2 prime, where y1 prime is equal to y2 and y2 prime is equal to t. And now this can go directly into MATLAB in the same way we just did. Okay, so now we can hop into MATLAB and we can go ahead and put our function into MATLAB. So we'll go ahead and write a little script. And we will once again expect to get time and the y values out of ODE 45. And we'll end up writing another function called dynamics. And we're going to have to give our initial conditions. So recall that we had y1 and y2, and that y1 is equivalent to y, and y2 is equivalent to y prime. And so our initial conditions for y of 0 was 2, and for y prime of 0 was 5. Go ahead and put those in there. We can define our dynamics function in the same ways we did before. And this time dy dt is going to be two elements, right? Because we've got y1 and y2. And so we'll set that up, we'll pre-initialize because it's a little bit more efficient, doesn't really matter too much in this small program. And we defined dy dt, or y1 prime, as being equal to y2. And so we set that. And then dy dt of 2 is equal to t. So we can set that up. And we can run it real quickly to make sure we haven't missed anything that actually does run, like naming it. Call it second order. And looks like it ran just fine. Alrighty. Let's go ahead and try to plot the values. We can do plot t comma y. And let's take a look at what we get. So you can see we got two curves out this time, and that's because it's plotting both y1 and y2. So we can take a look at what those would be by adding in a legend. Oh, there we are. And so there you can see both y and y1 and y2, which y1 again is y of t and y2 is y prime of t based on how we define them in our substitutions in the prior page. And so let's also compare this to the analytical solution. Go ahead and throw that in the legend. And our results from the analytical solution, we're just going to plot the same t-values that ODE 45 gave us out. And let's go ahead and plot them with maybe circles. I think it's like that. That way we can really see everything. And so as you can see, the analytical solution is tracking y1 perfectly. I also want to point out, I was talking a little bit about spacing earlier. You can see down here that MATLAB was actually calculating a lot of values before it kind of figured out how many values needed to calculate. So each of these points represents a point where MATLAB did a calculation in the ODE 45 function. And you can see that matches up perfectly. So next up, let's consider an actual dynamics problem. This is going to be a two-body problem. So let's say that you have a wall, and you've got a first body and a second body, and each successive body is connected by a spring. So we'll call this body 1, has mass 1, this one has mass 2, spring constants K1 and K2, positions X1 and X2, and natural lengths L1 and L2. Okay? And to make it even more interesting, let's say that there's a force being applied from something external over here. And we'll define that force as being equal to sine some timing constant t. And let's say that force is only applied between t equal to 0 and t equal to 15. This is all in seconds. Okay, so the first step is going to be to draw the free body diagrams of our system. So let's start off with mass 1. And so we look at that, it's going to have the force of spring 1, and then also the force of spring 2. And so the sum of the forces over that, as we would expect, is equal to, oh, I don't know why I wrote it 2. And that's going to be equal to negative x minus L1 K1 plus x sub 2. So essentially all we're saying here is that the distance from the natural length times the spring constant and negated to the spring, and then the difference between x2 and x1 minus the natural length of that spring, it would have been negative because it's pointing to the left, but negated, it's now positive, times the spring constant. All right, so now let's take a look at the second body. So body 2 is going to have the force of spring 2, and then also force external. So sum of forces 2 is equal to, as you would expect, mass 2. And that's going to be now essentially the same term as above. And then that external force. And as you noted above, this is only applied 0 to 15 seconds, but we'll just kind of take care of that later. We'll just leave it as is for right now. So we can further break this down by actually turning our accelerations into derivatives of x. So if we say x1 double prime, or in this class we've been using double dot notation, is equal to the same thing we have above divided by, I should really put like a little break there, divided by the mass of that first body. And similarly x2 double dot is equal to so same general idea. Okay, and so now we have to go back and do the same sort of thing we did with the last problem, where we start defining all of this in terms of its state space. So if we scroll on down, we can define our state space. Let's just turn it into y's just to make the notation a little bit easier. And this time, because we've got a physical system, we can actually talk about a little bit of the intuition behind what these different values are. So we'll define y1 as being x1, the actual position of that first block, and y2 as being x1 dot, y3 is x2, and y4 is x2 dot. Okay? And then now we can define the derivatives of our state space as well. So if we have y1 prime, y2 prime, y3 prime, and y4 prime, then that we can essentially do the same sort of derivative on the other side. So we have x1 dot, x2 double dot, I'm sorry, x1 double dot, x2 dot, and x2 double dot. And then now we know we need to have the differential equations for all this to put into MATLAB, and so we can do that. So you already know that x1 dot, which we have right here, is going to come from right here. And so we just say that that's equal to y2. The next one, x1 double dot, is going to come from up here. We have our equation, so we'll have, and as I write this, so this x1 doesn't necessarily have meaning in this state space, but we know that x1 is equal to y1. And we know that x2 is equal to y3, so we'll substitute that in right now. And then x2 dot, we already know is y4. And x2 double dot, we'll take from above as well, and we'll also do the substitutions for the y's. So x2 is y3, x1 y1, minus L2. Great, and so now we are ready to put this on over into our MATLAB.
Okay, so now we can go ahead and hop into MATLAB and put in all those equations we just solved for. So the first thing I'm going to do is I'm going to go ahead and copy in some values I have for the constants, which I've just more or less made up for the sake of this problem. I just didn't state them earlier. And so there are those. So we got the natural lengths, the spring constants, the timing constant, and also the masses. The next thing to do is going to be to define the initial conditions, and we didn't really talk about it, but let's just start off with static initial conditions. So no movement, which means that the spring or the blocks will be positioned at the natural length as well. So we have a y naught equal to the first block is positioned at the natural length of the first spring with velocity 0. The second block is positioned at the natural length of the first spring plus the natural length of the second spring, and also velocity equal to 0. All right, let's go ahead and define our function for the dynamics. And this one's going to look a little bit different because we're going to actually pass in all the different values for the various constants we'll use. So we'll have our standard t and y, but we're also going to have L1, L2, K1, K2, M1, M2, and also the alpha timing constant. Okay. So as with before, we're just going to go ahead and make a representation for our derivatives. It's pre-allocated. The first one, if you look back at our functions, was equal to y of 2. And that's just saying that that y1 prime equals x1 dot. Equations before. That needs a 1 right there. And then y2 prime was equal to that large equation we had before. I'm just going to go ahead and copy and paste that on in to make life a little bit easier. But essentially, that means that y2 prime, which is equal to the acceleration of x1, is negative y1 minus natural length 1 times the spring constant plus y3, which is the velocity of the second, well, the position of the second block, minus y1, which is the position of the first block, minus natural length, times second spring constant, all over the first mass. And then the third element, so y3 prime, we know is y4. And again, this is all just coming from the equations we wrote on the little blackboard in the prior step. And then dy dt 4 equals, and again, and this one has that force term that's only being applied for a portion of the time. So we'll start off by defining it fully like this, and then we need to actually put an if statement here. So this is only true if if t is less than or equal to 15. If t is not less than or equal to 15, then we know that we need to copy this on down. Then we know that we need to take out this force term, and so we'll just go ahead and delete that right there, and that should be good. Okay, so the next thing to do is put this all into ODE 45. And because our dynamics function now has all these extra arguments, ODE 45 expects a function with just 2 arguments, so we need to make an anonymous version of this. So we'll do that by typing in @ the 2 arguments we care about, the name of the function, and then all of its arguments. I'm just going to copy that on up. So what this is going to do is ODE 45 will actually see a function right here that has arguments t and y that get plugged directly into this dynamics function. And then the rest of the arguments will come from this line right here. So when ODE 45 is first run, it'll lock in the values of L1, L2, K1, K2, etc. That's powerful because you might want to have this all inside of a larger loop where you're trying different values of L1 and L2. Let's say you don't know what the system is. For the springs, let's say you don't know the spring constants. So you could try different values, compare it against some data you have, and see what's better. And so being able to anonymize functions like this can become really powerful. And we're just going to say we're going to simulate it over 0 to 30 so we can see that change, and we already have y naught. Okay. And then we'll just need to plot t comma y. And we'll put a legend on it so we actually know what's happening. So if you recall, y1 is x1, y2 is the velocity of x1, y3 is x2, and y4 is the velocity of x2. Okay. And we can give that a run and see what breaks. And there we go. So you can see we have a result. There's this nice and clean. It's kind of being stabilized by that force, and you can see right here at 15 seconds that force disappears, and the change. You can see there's definitely a change in the way that the springs are interacting. You can see that having 2 springs makes this a lot more complicated. There's a lot more of oscillating back and forth around each other, and because there's no friction, this doesn't really ever, or no damping or anything like that. It'll never decay. It'll just keep going. So we could plot this out for a longer time period as well. Let's do 60. And so you can see that, and then kind of what's cool about these different variables is I'll remove this, well, what we can do, so we can do like 4k equal to, well, for I equal to, let's say, 1 to 3, then we could have some k vect equal to and then I could say that, like, let's say we're just changing k1, so we'll do k vect at I, do that, and we'll add a title, and the title will just have the number in it. Oh, wrong notation. And so what this should do in theory is it should run through this loop 3 times, pulling out different values for k1, and we can see how they'll actually change. And so let's go ahead and we can run that. and that'll take a little bit longer because it's running now 3 simulations. Oh, you know what? I forgot to put a figure right here. And let's make this just run a little bit fast. Take this back down to 30. Okay. I'll run that again. And hopefully we get 3 plots this time. Sure. Okay. So if we look at our code, the first one will be a value of 2 for K1, the second one will be a value of 4, and the last one will be a value of 5. So we can put those all up here. Maybe-ish. And you can see that actually changing those values of K1 definitely changes the dynamics of the system. And that can be kind of interesting. So this is kind of where some of the power of solving this sort of thing in MATLAB comes out. In the comments below on the video, I'm going to put links to all 3 of the code files so you can check them out directly. I'll also put a PDF with all of the hand-drawn notes that we went through. I hope this was helpful. Let me know if you have any questions.